Hello everyone, this is a long overdue video. It is a quick and dirty introduction to PLCs. I hope to demystify them for you and give you some useful tips. To everyone on the fleet, if you think you have a video that you believe it teaches something useful for the community and it does not contain any classified or restricted technology, I will be happy to post it. Do not expect any monetary compensation, as the channel is a free channel and it complies with the Common License for Education. In the video, I try to simplify things as much as I can. However, PLCs are an advanced topic, so the viewer is expected to have a good solid understanding of basic electrical principles. Also, check out video 35, compressing melting units. Those units use PLCs, and I cover PLCs in that particular video. This video is more theoretical, and video 35, it is more practical. To understand the convenience of PLCs, let me introduce you to this relay. Before PLCs, many cargo elevators and some motor controllers were designed to be smart, to make certain logical decisions based on input from users or sensors. Many relays were interwired to accomplish these logic decisions. Here is a picture of one of those smart motor controllers. They were a nightmare to troubleshoot and broke a lot. The principle was simple. They will take some inputs either from users or from various sensors. They will actuate according to how they were wired to make a logical decision, and a wire output will be put out to start, stop, or activate equipment. Then came the savior, the PLC, a simple small box that simplified the whole thing. And since computers are great at making decisions based on logical preset rules, an interface was created to be able to collect inputs and deliver it to the computer. And a second interface was created to allow the computer to control industrial equipment via relays, transistors, triacs, or voltage or current regulators. How does this PLC computer looks like? In reality, it is a microcontroller, and it is nowhere as powerful as any computer that you might use, but it is powerful enough to control most industrial equipment. This type of setup needs a power supply and a network card or type of network card to be able to communicate to other PLCs or a network. The objective of this video is to provide a practical high overview of PLCs. The acronym PLC stands for Programmable Logic Controller. To easier understand PLCs, let's look at this block diagram. This PLC is divided in 4 modules. At the bottom, the power supply, it is actually 2 power supplies in one 24-volt DC and a 5-volt DC. The 24 volts is used to power the output module to the right and the input module to the left. The module to the middle is the computer, and 5 volts is more than enough to power it. As any computer, this computer has memory, and the ROM memory, which stands for read-only memory, is a permanent memory that stores all kinds of instructions even if the PLC is powered down. The other type of memory, RAM, which stands for random access memory, is a temporal working memory that disappears as soon as you power down the equipment. Compare this to your smartphone. ROM is the type of memory that ensures that when you start the phone, it loads the proper operating system so you can use the phone. And if you open Facebook, it gets loaded up on that working random access memory, but if your phone powers down, it disappears. As you can see, this PLC has an Ethernet card. That means that if a computer gets plugged into this PLC via an Ethernet cable and the computer has the right software, it can communicate with the PLC. Lastly, I want to point out that the central processing unit is what executes the PLC program. PLC programs can be written in multiple languages. However, the most popular one is the ladder logic because it resembles a motor controller schematic. And ladder logic is flexible, easy to learn, and well understood by electricians. However, as the younger generation keeps learning programming languages like Java, Python, and JavaScript, these languages closely resemble structured text. Therefore, we will see more structured text programming controllers written in the future. There are two major types of PLCs, the compact or fixed type, and this, the CPU, the input, the output, the power supply, are all inclusive. The limitations of these ones are that they have a set amount of inputs and outputs. They are cheaper and suitable for small projects. However, in the fleet, you are more likely to encounter the modular PLC. The designing engineers will add modules as necessary, and faulty modules can be replaced in the field. Here, the power supplies are to the left. The communications module will be connected to the network, probably via Ethernet, and things like encoders, temperature sensors, proximity sensors, push buttons, and switches are connected to the input modules, and solenoids, alarms, contactors, signaling lights, those are connected to the output modules. Typically, several times per second, the PLC will ask the input module the status of its connected inputs. Then the PLC evaluates and makes a decision based on this program and will determine what needs to be energized or de-energized via its output module. You cannot connect outputs to an input module or vice versa. Input or output modules can be either analog or digital modules. For example, thermal sensors vary their resistance depending on the temperature. Here I am implying that the analog input module receives a range between 4 to 20 milliamps depending on the temperature sensed by the sensor. However, if the module is an analog output module, it is able to provide a range of voltages for the variable frequency drive on the right based on what is ordered by the CPU. On the lower left corner, there is an encoder. Encoders can only produce digital signals, therefore can only be connected to a digital input module. Likewise, relays, they need full voltage or no voltage. Voltages in between could degrade the relay. Therefore, a digital output module is best suited to control a relay. Now, strictly speaking of digital output modules, there are two types, the solid state and the relay type. Either one does the same job. When the CPU sends a trigger signal, they just conduct. In this case, the solid state device uses a transistor, so therefore it can only control DC currents. But if it was a triac type, it could use or conduct AC. On the right, relays, they can conduct either AC or DC. Analog PLC modules are configured for different analog signal types, whether they are voltage or current ranges as shown, or millivolt ranges for thermocouples. If you were expecting a particular voltage range and you needed to verify, you could use a multimeter to take a set of readings just as shown. As you can see, analog modules do not have any indication lights. However, digital modules do have indication lights. I love these indication lights because all I have to do is identify the switch, press it, activate it, or actuate it, and then I'll have to just look at the PLC module light. If it comes on, that means that the switch is good. Of course, that is assuming that I'm dealing with normally open switches. Similarly, if on the output, I will be expecting the contactor to be energized, and if I look at the module and light 0 was off, I will not even bother to look at the contactor. Instead, I will focus on figuring out why the programmable logic controller is not sending the command. However, if light 6 was on, but the light bulb was not on, I would replace the light bulb or take voltage readings at the light bulb socket. If there was no power there, then I would ensure that I have a good connection from the module output 6 to the light bulb and the light bulb to the other side of the power. Now, could it be possible that it would be a faulty contact number 6 inside the output module or its associated coil or transistor or triac, depending on what type of output module it is? It is possible. If that were the case, the whole module will have to be replaced. See a live demonstration, check out video number 35. Compressing melting units or CMUs, they use PLCs. And I cover PLCs on that video. When dealing with relay type output modules, keep in mind that some of the output relays may be configured as normally opened and the other ones as normally closed. Therefore, the normally closed should read shorted whenever the system is de-energized, and they should open whenever the associated light indicating light turns on. Let me repeat that. In this scenario, number 3 is normally closed. When its associated light is on, this contact should open and not conduct. Now I will show a short video that I found online. Notice that this technician will test terminal 1 normally open and terminal 3 normally closed. Terminal 2 is the one that provides power to the relay, so it won't get tested. This is the signal that is controlled by the CPU.
Normally open number 1 should be on. Okay. And then terminal number 3, normally closed, should be off because the switch has changed. Terminal number 4, normally open, is now closed. Number 6, normally closed, so that should be off. 7 should be on.
Besides troubleshooting the inputs and the outputs, which is where you're going to find the most problems, ensure that the power supply is doing its job. A 24-volt power supply needs to provide 24 volts, not 21, not 22, not 20. Electrical noise and interference is a big problem, so keeping the equipment close is very important, as this will help to create that Faraday cage to protect the internal components. If you ever replace a cable that is shielded, make sure you replace it with a shielded cable. If you do not, the equipment is going to work, but sooner or later, EMI interference might start bugging the system and it's going to be really difficult to troubleshoot. This interference can corrupt the memory within the chip. Remember that shielding, grounding, and proper power conditioning are the best way to fight EMI and RFI problems. Some of you might be wondering, how does the PLC work at the CPU level? I will keep it simple by stating that in memory, it is divided by thousands of pieces, which are indexed by memory addresses, which are sequential, and all kinds of stuff is stored in there, which you don't have to worry about. However, a few positions in memory are indexed to the inputs and to the output. What does this word indexing to the input and the output means? It is simply a fancy way of saying that the state of an input will eventually be updated to a position in memory that is referenced by a particular memory address. In this example, let's assume that this memory is addressed to the input number 2 on the left. When its associated push button sends a signal, this voltage will be represented with a logical 1 at the assigned memory address. The computer periodically checks these addresses and takes actions based on the predefined rules that it has in its program. If we assume that this other address is associated to the actuator, eventually the computer determines that a 1 needs to go there. Once again, that decision will be made based on its logical program. And since this location in memory is indexed to position number 6 of the output module, which corresponds to the actuator, and since there is an internal scanner, which periodically will check the corresponding memory address to the output module, and if it finds a 1 in there, it will notify the output module to energize the triac number 6, causing to send a signal to energize the actuator. I want to make sure that there is no misunderstanding. The output module gets one line of power from a transformer in this case, and when it closes contact number 6, it sends power from that same line that took from the transformer to energize the actuator. Note that the actuator already have the other leg of power from the transformer. Once the circuit is completed, the actuator will extend in this case. Both the input and the output module, they get 24 volts from the power supply so that they can function. But the output module also takes full voltage as a common line so it can redistribute it to energize components that are attached to it. Let's look at a sample program to better understand the true power of PLCs. We'll use a ladder logic to control a very simple elevator. Here is the elevator trunk and now the platform. The platform can ride up and down between the first and second floor. When the platform travels downward, it should stop on the first deck stop. If this were to fail, a backup stop called first deck over travel is only meant to be engaged under an abnormal condition. When the platform travels to the second deck, it needs to be stopped by the second deck stop. And only if this stop fails, then the platform will continue, but it should get stopped by the second deck over travel. Only equipment is supposed to ride on this platform. Therefore, we put the controls outside. The first and second deck only have 2 push buttons each. One is called to send, and the other one is an e-stop. The first deck send only sends to the second deck, and conversely, the second deck only sends to the first deck. When any press send is pressed, an alarm sounds for 5 seconds, and as soon as it stops, the platform starts moving according to the command. We also want a counter to increment every time the platform arrives at the second deck. And at every 100 arrival, we want the PLC to disable the platform operations until maintenance is performed and normal operations is restored by turning a switch key located next to the PLC. For maintenance, I included a manual up and manual down push button. These 2 push buttons allow technicians to move the platform without the restrictions imposed to the send button. Lastly, the platform is moved by a large motor that is controlled by either the up or the down contactor. Here is an overview of the likely circuit that I want to share with you to discuss the PLC ladder logic. So I did not include or bother to include circuit protection for this system, or if you notice the contactors, they are not interlocked with each other. So I covered that in different videos. The objective of this is PLCs, and so pretend that over here we got 3 lines of power for 40 coming in. They go straight into the contactors, and notice that this contactor has 2 leads that are reversed compared to this one over here, and that is so that the motor will rotate in an opposite direction than the top contactor. The secondary of the transformer immediately powers the one side of the loads, which is the alarm and the control side of this contactor and the control side of this other contactor. The other leg of power, it is supposed to be supplied by the PLC. The PLC, if you will, it has 2 legs of power. It does have 2 legs of power because, you know, that's how it comes on. It's 110, and it has its own internal power supply that it will convert it to the 5 volts and 24 volts required for different systems. Although this is a this is a unit PLC, so it might just only have 1 power supply for everything. Now, notice that inside there, actually the way how it's wired, assuming that it's a relay, it's so we got power coming in here, this leg of power over here, and when it closes, it just transfers that side to this side over here, and that's how it gets power to the other leg to control, to energize these things. The PLC decides when when this load gets energized based on what the instructions of the program and the inputs. The inputs over here, I put a blue line indicating that it's 24 volts that the PLC is providing. This is not the only allowable solution, especially if the PLC has what is called optocouplers. But anyway, as soon as you press a button over here, the assumption or the disclaimer is that all of these push buttons and all of these switches are normally open to include the key switch. So whenever somebody presses a switch, really what is happening is bridging the 24 volts positive into this connection over here, taking it to the PLC. I drew them to the back of it, but in reality this would be more like the inputs. This screws over here, and this over here will be the outputs. But trust me, it's a much more cleaner way how I drew it right now. One last thing before we get into the ladder logic. So the input module has different components that are attached to it, and it gathers the statuses of all of those components, and periodically it populates certain memory addresses. Those same memory addresses, some of them will be assigned or tied to certain components within the ladder logic, and those components will behave or change the status based on whatever it is sitting on that particular memory address. So the memory address is affected by the input module, and the input module puts a value over there that corresponds to the position of a switch or sensor or whatnot. And in turn, the address, it determines what the outcome is of the particular associated component within the ladder logic. This on the right is a ladder logic program. All the components are virtual components. They are not physical. They only exist in the computer memory. However, a few of them are associated with real components in the world. Let's identify them first. In yellow, I will highlight the first deck and second deck over trouble switches. Green, I will highlight the first and second deck switches with their associated virtual components. I will use purple to identify the key switch and the manual down and up push buttons. And while I was marking the two lower virtual components, I realized that I had missed two yellow components. And in orange, I will mark the send push buttons. On the left, I only had the inputs. I didn't include the outputs, but the outputs also are partnered with virtual components. In this case, they are virtual relays, the alarm, the up, and the down. When these virtual relays get energized, then the alarm or the up or the down contactor will get energized in the real world too. PLCs support counters, timers, interrupts, and many other features. Here we have what is called a CTU or counter up. It is a digital counter that only counts on the rising edge of a signal. What this means is that when the signal changes from 0 to 1, that is when it counts, regardless of the length of the signal. Here, normally open stop switch number 2, which is mapped to the second deck stop switch. When the switch gets flagged, it will cause the counter to increment by 1. Next, the R connection of the counter, which stands for reset, it is activated by the normally open virtual contact called reset key. This virtual contact will close when a technician puts the key in and turns on the switch. When programming during the options, PV will be set up, in our case, to 100. Every time the CU receives a signal, CV will be incremented. And when CV reaches 100, it will be equal or greater than PV, and this will cause Q to energize. The 1 out of Q will cause the coil do maintenance, at least that's what I call it, to energize, and that will cause its associated contact to close. And if the key is not inserted and turned, that is going to cause the maintenance relay to energize, and that relay will cause its associated normally closed contact to open. This will disable S1 and S2 from being able to control the elevator. If you notice, S1 and S2 relays are all the way up here, and they are located in a direct path that either the send push buttons are controlling or trying to energize. Notice that the over trouble switches, if flagged, they will open de-energizing OT contactor or coil. Oh, I made a mistake. This OT contact needs to be normally open. There, it is fixed. Clearly, OT needs to be energized for its associated normally open contact to be closed. If OT coil de-energizes due to either of the over-trouble switches getting flagged, then OT's associated normally open contact will return to the normally open state, effectively disabling the ability to do a upsend or downsend command. Now let's talk about the time delay. Notice that the preset has been set to 5,000 milliseconds, which means 5 seconds. As the timer counts, the accumulative value will hold that value. Some programs might use that value, but our program will not. Notice the name that I assigned to the timer, my timer. When the timer is counting, my timer associated contact will close. This will cause my delay relay to energize, and it will close its associated normally open contact, effectively energizing the alarm relay, which is mapped to the output module, which it will sound for 5 seconds, because after 5 seconds, the time delay will expire, restoring again or opening my time contact and therefore opening my delay contact, de-energizing the coil for the alarm. Notice that the manual app only has 2 restrictions. The platform cannot be stacked all the way up and it cannot be going down. Otherwise, pressing the manual app, it will close the associated virtual contact, energizing the app man coil, and this coil will close its associated normally open contact, energizing in this case the down command. And yes, I got those 2 backwards. I just went ahead and fixed it. I must tell you that the ladder logic circuit works a little bit different than a regular motor controller circuit. Let's send the elevator down so I can point the differences. At the second deck, let's press the send button. As expected, normally open virtual contact send 2 closes energizing coil S1. Each set of line instructions are called runs, and they are read from left to right, top to bottom, because this is how the computer will read it. In this case, the computer will continue evaluating ranks 3, 4, 5, and eventually to 6. There, it will close normally open virtual switch send 2, which this one initialized the timer. Then the computer will continue evaluating every other rank below, and it will not make any more changes. However, computers run on cycles, so in the next cycle, which is a few microseconds later, it will start evaluating all the way from the top. It will run into S1 and realize that it is energized, and it will start closing all the S1 switches. During this second cycle, so 2 S1 switches will be closed along with my time number 1. And this is because the timer delay was initialized in the previous cycle. This cycle of evaluations caused the downsend command to be enabled, but its associated normally open contact is not yet updated. Notice that during the third cycle, the virtual my delay contacts are actuated. This means that the downsend virtual contact will not have a chance to close its associated contact. And in the next cycle, the alarm memory address space will be updated. And when the output module scans that memory address, it will update the output associated with the alarm. Let me remind you that all of these things happen in a fraction of a second. So from a point of view, these things are instantaneous. While the alarm is sounding, I expect the user to let the push button go. So I return the state of the associated virtual switches for the send 1 button to the normal de-energized position. After the 5-minute time delay, my time 1 will expire, open its contact, de-energizing my delay, and delay will open its contact, de-energizing the alarm. And yes, this will take a couple of cycles because the computer is constantly scanning first run, second run, third run, all the way to the last run, and then it starts all over again. And the truth is that computers like to do the same thing over and over and over and over and over. Of significance is that the my delay normally close contact returns to be close, and this is where the fun ride begins. After 2 cycles later, the virtual down solenoid will energize, and when the output module being formed, it will energize the physical down relay, sending the elevator downwards. As the platform leaves the second deck, it will unflag the second deck stop switch, and this will cause its virtual associated normally open contact to return to the open position. The elevator will continue down until it flags the first deck stop switch. This will cause its associated virtual contacts to change their state. And it follows the domino effect of losing power. So S1 loses power, opens its contacts, therefore the down center loses power, opens its contacts, and the down gets de-energized, telling the output module to de-energize the down contactor, stopping the elevator. And now you can say that you have seen PLC ladder logics in action. If I would have added 2 speeds to this elevator and 2 switches per deck, one for slow and one for stop, it would have made this schematic very complicated. And if we were to add more decks, it would be even more complicated. Look at this setup. It is very elegant, very few components. And PLCs, they tend to be very reliable. And one of the main advantages is that we can simulate as many virtual components as we need to create different circuits. And you saw how easy it was to implement a counter. I would like to add that if you have a spare contacts on your output module, for example, you cannot just simply switch it, because when they write the program, they define which ladder logic outputs are going to correspond to particular output module contacts. Some of the more advanced PLCs, they let you do that, but you still need to have permission. And the truth is that by making a simple change within the program, you can ruin the whole program or cause the machine to bypass safeties and have erratic operations. Field technicians are not to program in the field. When programs are written, they are tested with varying conditions to ensure that it works as expected.
Oh gosh, this was a really long video, and if you're still sitting over here watching, I got a few more nuggets for you. First, one time I had to replace a PLC module, and according to the instructions, I was supposed to power the module, hook up a computer to it, and go into my browser and type in an HTTP address number so I could access the HTML configuration file within the module. I tried and it did not work. But when we put it into the system, we were able to access it through the computer. That was the network computer that engineers used to take readings on different equipment. I searched on the internet and I could not find an answer of why it didn't work. Last year, around July or August, as I was studying for my CCNA 200 to 301, I became aware that if you're trying to plug in directly with your computer to a Ethernet port, first your computer needs to be in the same subnet mask as the device's IP address. When you plug a computer into a network system, it gets an IP address from the Dynamic Hosting Configuration Protocol, or DHCP. And if it doesn't find a DHCP server, your computer assigns itself a address 127.0.0.1. So you will need to go into your network settings in your computer, select the manual address configuration, and assign to your computer an IP address that is in the same subnet as the PLC module that you are trying to communicate. The module is going to have an IP address that falls within any of the INA private addresses. For example, 192.168.10.10 with a subnet mask of 24. That's very typical. When you assign an address to your computer, the first 2 digits, just keep them the same. And for the 4th digit, you can choose any number between 1 to 254. minus the number that is already assigned to the module. For the subnet mask, just try default /24. Keep in mind that computers are meant to be connected to switches and not connected directly to computers. So it's most likely that you're going to need what is called a crossover cable. You can buy one from the ITs. If you do everything right, you should be able to set up into your computer, type in the HTTP address on your browser, and you should be able to interact with the module. If you are able in this type of pickle, just show this part of the video to the ITs and they will know exactly what I'm talking about. The second nugget that I have for you. Now, do not quote me on this. Don't say that YouTube told me to do this, but on USS last ship, from time to time, the PLC in the CMU, one of the CMU units, will lock up, and powering down and restarting the equipment, it just didn't cut it. When tech support came on board, I saw them open the PLC CPU module. They looked for the microcontroller. If my memory doesn't fail me, I think it was a PIC 116F877 Alpha. I know it well because in those days I used to build projects using this microcontroller. I myself use C language to write programs for these chips. So I assume that the manufacturer didn't even bother to use ladder logics for this type of chips. And ladder logics is a pain when compared to C. Anyway, the tech rep, they came in and they literally just pull out the chip, waited a few seconds and pop it back in. These microcontrollers are not meant to be soldered. You just simply, or they sit on a chip housing. The problem happened again on their way, and one of my technicians tried to pull it with some pliers, and he broke one of the little legs. I put in a paper clip next to it and soldered, cut the excess, and the microcontroller worked just fine with the paperclip leg as a pin. Keep in mind, the program is burned inside the chip, so replacing the chip with a new one is useless because it does not have the program. If you were to have the programmer, which they cost about $10 on eBay, you could import the program into a computer and burn it into another fresh chip. But that's way beyond what you are expected to know. And my last word of advice is I haven't written a PLC program in a very long time and I already forgot how to use the software. There are multiple software downloads that you can use on your computer to practice PLC programming. So I had the bright idea to use Paint to manually create a ladder logics like I did. Big mistake. Even though I was careful, first I did it on paper and then I did it on Paint and I thought I was good, and you saw how many errors I had to change as I was going through the video. I should have just simply take the time, watch an hour or 2 hours of PLC programming videos of a particular platform, download the software, practice for another hours, and then write this program. The program that I showed you guys. It would have saved me so much time. So yeah, it was stupid of me to have written the PLC program by hand. And I chose to design a PLC program for an elevator, simple elevator that is, because what I found online, it really didn't had all the options combined and simplified into one simple short program. If you're still watching, thank you for hanging out until the end of the video.